Thank you very much. Hello, Bangalore. Happy Valentine's Day, everyone, and welcome. Thank you for joining in today. My name is Tanmay Bakshi, and I love to explore technology. More specifically, I love developing and working with algorithms that allow machines to think for themselves and understand abstract concepts and data that up until now, only humans were known to be able to understand. Basically, I like to take human-like intuition and put it into our machines. And I'm sure that you've all probably guessed it at this point. You've caught on to the memo. I'm talking about the technology that we're all practically dying to incorporate in all of our systems today. And that is, of course, artificial intelligence, cognitive systems, and machine learning technology. And I do know that that sounds quite interesting, but just before I get into it, though, I'd like to start off by saying a huge thank you to the entire team at IBM Code Day 2018 for putting together this conference, putting this developer community under one roof, and inviting me here today. This is very, very exciting. In fact, speaking of the developer community, what better way to start off today than to be showing you a sneak peek into the technologies, not just the present, but the future as well. Which is why today, I've got 3 great examples lined up for all of you. And not just examples, but today I'm actually going to be coding and showing you how to use these technologies in action. And I'd like to start off with one of the technologies of the future, something that we can expect to be using in the next few decades. And that is, of course, quantum computing. In fact, just before I begin, if you'd like to find out more about what I'm actually talking about, and maybe even follow along as I actually code in action, you can head over to ibmq.tanmaybakshi.com on your phone, on your computer, wherever else you want to, and you can actually follow along with me right now. But before we can talk about quantum, though, we have to talk a little bit more about traditional computing in the first place. So imagine this. This is actually an example by IBM Research. So let's just say you've got a deck of playing cards. Now do this. Choose 4 cards, say 1 queen and 3 aces. Now do this. Shuffle those playing cards. Now take a look at the cards and try and find the queen. How do you do it? Well, with a traditional computer, you do it like this. Is the first card an ace? Yes, it is. So that's not a queen. Well, maybe the second card's a queen. No, that's also an ace. And then you look at the third card. Maybe that's a queen, and that turns out to be a queen. Now remember, a traditional computer can do that in quite literally microseconds, because it's a very, very simple equivalency task with only 4 cards. But imagine you've got a more complex problem with even more data points that add up exponentially. Say, the traveling salesman problem. A traditional computer can't handle that kind of computation. But with a quantum computer, we can most probably actually do that in just a few operations, and do that within seconds. In fact, in order to demonstrate how this is such a powerful technology, let's take a look at the example of one of the most famous quantum experiments ever done, the double slit experiment. I'm sure that you all know, if we were to take, say, a liquid, and if we were to put a little board in it with 2 slits, and if we were to put a wave through it, some of the waves would bounce back from the slits, but some of it would actually go through the 2 slits, interfere with itself, and if on the other end of the screen you were to measure the intensity of the wave at every point and graph it out, this is what the intensity would look like. It's strongest in the middle, and towards the sides, or towards the top and bottom in that diagram, it gets smaller and smaller, or weaker and weaker. However, if you were to do that with a solid, you would expect a different result. So you've got a marble projector, and you throw marbles at this board. Some of them would just hit the board and bounce back, but some of them would actually go through the slits. And once they go through the slits, they'll create 2 lines on the board itself, so you can take a look at those 2 lines and where the marbles actually landed up. But if you were to scale that down from a macro scale to a micro scale, you'd expect the same result. Say you do that with an electron gun instead of a marble projector. You'd expect, because these are particles, to see 2 lines of electrons. But astonishingly, that doesn't happen. Instead, you see an interference pattern. Now that sounds very interesting, and it's because of an effect called wave-particle duality. What that means is when the electron leaves the electron gun, it's no longer a physical particle. Instead, it's now just a non-physical wave of probabilities of where it may be in the universe, because it's not interacting or being observed by anything else in the universe. That wave goes through the board, interferes with itself, creates an interference pattern of probabilities, and as per the Copenhagen interpretation at least, when the wave function collapses when the electron hits the screen, the universe will collapse down onto one decision and decide where that electron is. And if you were to actually put a camera and try and see how that happens, you no longer see that interference pattern because the electron is being observed by something. What's happening is because it's interacting with something in the universe, it never becomes a wave. It remains a particle, a physical particle. And now this itself is powered by some very, very interesting quantum mechanics, including superposition, which means that if you don't measure or observe a quantum particle, then its properties can be in numerous states at once. Like, for example, the particle spin. Let's just say a particle spin can be up or down. Now, there's a 50-50 chance of it being up or down. And until we actually measure that particle, it is technically in both states at the same time because it's not being interacted with. And similarly, entanglement means that no matter how far apart two quantum particles are, if they are entangled, then the moment you collapse the wave function of one of those particles, you instantly collapse the wave function of the other particle, and you can find out properties of that particle. In fact, it's so instantaneous that even Einstein called this effect spooky action at a distance. But anyway, enough talking about quantum computing. Now, let's get to quantum in action. And in fact, in order to demonstrate this, I'd like to talk about IBM Q. IBM Quantum allows you to run quantum computers that IBM actually has in their Yorktown research lab in the cloud. So you can build quantum applications right now, today, entirely for free. But now, without any further ado, let's get into a demo of IBM Q in action. Let's take a look. All right, so as you can see on screen right now, we can switch over to my demo Mac here. And now this is called the IBM Q Experience. On this webpage, you can find out more about IBM Q and how exactly quantum computers work. There's a community page where you can share your your programs, your quantum programs, with the rest of the community, and you can find out more about what others are developing as well. All right, so as you can see in the composer, we've got a few different quantum computers that IBM allows us to use, including the QX4 and QX2. In fact, you can even take a look at a diagram of how all the individual qubits or quantum bits actually interact right over there. And so with that diagram, you can find out what kinds of programs you can make. Now, the QX4 machine, which is currently under maintenance, is what I'd like to use. But doesn't matter if it's under maintenance because we can even simulate quantum programs as well. All right, so what I'm going to do is I'm going to start off with a very simple example. I'm going to do something that proves superposition. So I'm going to put the first qubit over there, as you can see on that line, into superposition by dragging a Hadamard gate onto it. It's that simple. I've now put that qubit into superposition. And what I can do after that is simply take this operation over here and measure the qubit that I've just put into superposition. Now remember, when it's in superposition, it has a 50-50 chance of the value being a 0 or a 1. And so if I were to run the program, say, 1,000 times, then it should give me an equal number of 1s and 0s, or at least an almost equal number of 1s and 0s. I'm going to click on Simulate. I'm going to give it an experiment name. And theoretically, if this works out, as you can see, it did. What the simulation gives us is the value 1 45% of the time, and the value 0 55% of the time, which is very, very close to 50-50 chances. All right, so as you can see, that's an experiment that proves superposition. But now let's take a look at an experiment that proves entanglement. All right, so let's reset this over here. I'm going to remove those gates. This time, let's put the second qubit into superposition. And let's go ahead and use this operation, or this gate over here. And let's actually put the first qubit in entanglement with the second qubit. And then I'm going to measure the first qubit and the second qubit. All right, so now again, remember, when the second qubit is in superposition, its value is a 50-50 chance between being a 0 or a 1. And because the first one's entangled with the second one, its value should always be the exact same. So 50% of the time, we should see a 0, 0 output, and 50% of the time, we should see a 1, 1 output. We shouldn't see any other kind of output. And as you can see, we see 0, 0 46% of the time, and 1, 1 54% of the time. And so that was a quick demo proving superposition and entanglement and how that actually ties in with quantum computing. We can run back over to my presentation now. But that was a very, very simple demo of how you can use IBM Q today. And so that concludes what I had to say about IBM Quantum. Again, you can go over to ibmq.tanmaybakshi.com to learn more and use the IBM Q Experience. All right, so back to my slides now. All right, so now that I've been able to show you a sneak peek into the very, very exciting technologies of the future, I'd now like to take us all a step back for a minute. And now I'd like to show you a glimpse into one of the most powerful and exciting technologies of the present. And of course, as you know, the technology that I'm talking about today is deep learning technology. But before we can talk about deep learning, I actually have a question for all of you. And this is a question that I was asked yesterday as well. Think about this. What's one thing that you don't like about code? Think about it. Well, yesterday, when I thought about this for a minute, I realized that the one thing I don't like about code is the fact that it's very repetitive. There's a lot of repetition when you're programming. And especially when you're doing machine learning development. Because when you're designing a neural network, you don't care about the code. You only care about the techniques and the algorithms that go behind that code. And so that's why today I'm really excited to be talking about a brand new initiative by IBM called IBM Code Patterns. In fact, again, I'm going to be showing you IBM Code Patterns in action today. And if you would like to follow along and find out more about the code patterns as I talk about them, you can head over to ibmcodepatterns.tanmaybakshi.com. All right, so now code patterns, what are they? Imagine code patterns as basically little building blocks. They are building blocks that you can combine together with your own custom code. And when put together, you can create very powerful applications with a fraction of the repetition. You have to do hardly any of that repetitive code that would have held you back in the past. And then the best part is, you're not even just limited to IBM Cloud products. You can also use all of your open source tools that you currently use in your applications. So you can power your apps with practically anything that you'd like. And of course, though, you also have the powerful IBM Cloud tools at your disposal. You can make use of Watson Machine Learning, the Watson Data Science Experience tools. You can even use the actual Watson APIs on the IBM Cloud. You can use technologies like Power AI, and so much more. In fact, there's a huge list of all the different technologies that these code patterns actually support. And they're not even just limited to machine learning. There is so much more than that. But today, though, I've chosen one code pattern that I think we'd all be very interested in today. And this code pattern allows us to use a technique called transfer learning to actually create a deep learning model which learns how to classify images of houses with and without swimming pools. Again, very simple example. But the technology is interesting because we've only got 40 training images and 4 test images. And so it's going to be a challenge actually pulling this off and making sure that we have enough accuracy at least to test out with and make sure that we're able to get some good results. This is the technology stack that we are using today. We're using a Jupyter notebook on top of Python, of course, using TensorFlow in the back end for the actual deep learning model training, and all of this is sitting on a bare metal IBM Power AI server with an NVIDIA Tesla P100 GPU and IBM Power 8 chip for you. But then again, though, the best part of the code pattern itself is the fact that it's extremely customizable. I can take the code that they've given me that's powered by TensorFlow, and since I'm much more comfortable using Keras, I can almost immediately port that code over to the Keras deep learning library based off of the code that they had actually prepared for me in the code pattern itself. And so now, though, without any further ado, let's get into a demo of the system in action and how you can actually build a transfer learning-based deep learning system using IBM code patterns. Let's take a look. All right, so we're going to switch back over here. And now this is the code pattern that we're going to be using today. Now as developers, as for us developers, there's one button that stands out here, and that's the Get the Code button. So I'm just going to click on that, and it's going to bring us over to a GitHub repository. This GitHub repository actually has all the different code, and in fact, it actually also has steps as to how you can actually complete this code pattern and get it running for yourself. The first step is to get 24 hours of free access to the Power AI platform, which I've already done. In fact, yes, you can actually get 24 hours of free access to IBM Power AI, to this extremely powerful system. After that, though, we're actually going to set up and start using the Jupyter Notebook. Before that, though, I'd like to show you that I've actually SSH'd into this Power AI system that I was given quite literally instantly once I signed up. And now I can even do things like, for example, NVIDIA SMI, to show you that we are indeed running a Tesla P100 GPU on the server. We can run free -G, we're running 128 gigs of RAM, we can run uname -A, and we are indeed running a Power PC system over here. So as you can tell, we are working with a very powerful system, and through this SSH tunnel, I've also been able to start a Jupyter session. Now inside of this Jupyter session, your next step will be to actually clone that Git repository down onto your server. But I've already done that because, again, I don't want you to have to watch paint dry. All right, so I've already cloned this GitHub repository, and inside of it, you can see quite a few different folders, but the one that we're most interested in is the Notebooks folder. If you go inside, you can tell that the IBM code pattern gives you this great code to start off with, so you can actually begin in a very simple way. It shows you all the different steps with extremely detailed documentation, and in fact, these are some of the examples of the data. And if we were to actually go to the very bottom of the notebook, I can show you some more examples as well. This is the image classification that we're trying to do. We're trying to find houses with these types of swimming pools and the houses that don't have these swimming pools. And again, only 40 training images, but if the deep learning model works nicely, we should be able to actually have a shot at this. All right, so now I'm going to go back over to the Jupyter interface over here, and I'm actually going to upload a file. Now this file is actually the Python notebook that I've already prepared, which is a ported version from TensorFlow to Keras. Now this took me at maximum 20 minutes to make, and I'm actually exaggerating that a little bit. So that took me around 20 minutes to make, and if we actually go into this notebook, as you can see, I was able to take that TensorFlow code and almost line for line translate it into Keras code, which is what I am comfortable with. And so now, though, I think it's time to actually run this code and show it to you in action. All right, so what I'm going to do is, again, using the simple Jupyter interface, I'm just going to click on Run All. And what it's going to do over here is it's going to import TensorFlow and Keras. It's going to get that done. And then it's actually going to download the Inception deep learning model. Inception is a deep learning model created by Google. And this deep learning model, extremely powerful, is actually trained on the ImageNet dataset with around 10 million training images on 20,000 different categories. We're going to be taking the knowledge that this neural network already has, and we're going to be fine-tuning that knowledge to amplify its skill of actually recognizing houses with and without pools. This is called transfer learning. As you can see, it's done downloading and preparing that model, and it's even done actually setting up the data, and it's also almost done training. Again, we're running on Power AI with very little data, and so each epoch only takes around a second. And as you can see, on the fourth epoch, we were able to reach 100% accuracy on the validation dataset. Again, that's a little bit misleading because we've only got 4 testing images, so the model doesn't really get a chance to show off the noise that it's actually learned or what it hasn't learned in the first place. But what this proves is that within 20 minutes, I was able to create a deep learning system powered by Keras with a TensorFlow backend, and I didn't need to do almost any of the work. The code pattern did it all for me, and now I can either swap out the data for my own data, or I can take the machine learning model that this has just given me, convert it to Core ML, apply it to a mobile application. I can deploy this on Node.js on the web, or do whatever else I think is necessary for my application or for my specific use case. Imagine all the repetitive code that's been taken away because I didn't need to do all of this. And now I, as a developer, can focus more on the actual technique of implementation and the algorithms behind this rather than focus on all of the code and actually getting the algorithms to work. All right, I hope you enjoyed that demo of IBM Code Patterns and IBM Power AI in action. Now we can switch back over to my slides here. All right, so now that you've seen a demo of IBM Code Patterns in action, and we can, of course, switch back over to my slides, please. Perfect. All right, so now that you've seen a demo of the IBM Code Patterns in action, though, I'd like to talk about another very, very interesting technology. In fact, it's the technology that powered the demo that I was showing you today. And this technology is called IBM Power AI. Again, I'm showing this to you in action, and so if you'd like to find out more about Power AI, you can go to linuxonpower.tanmaybakshi.com and find out more about how it works. But again, getting back to the IBM Code Patterns, this was the bare bone that was actually powering and allowing us to use the code pattern. It's the IBM Power AI which provides us the Tesla P100 and Power 8 CPU to work with. But Power AI itself isn't limited to just bare metal servers that you as a developer are provided to build your applications. There's a lot more than just that. In fact, there's also a tool by IBM Power AI called Power AI Vision, which I am very interested in. Why am I so interested? It's because it solves the #1 problem when working with deep learning. And that is the problem of the lack of labeled data. I'm sure we've all experienced this. And that is, it's very, very easy to get unlabeled data. If I wanted to build a self-driving car and I wanted to get videos of people driving their cars, like a camera in the windshield, I could easily do that. That would take me a few days and I'd get gigabytes of data, terabytes maybe. But the problem is getting labeled data, because no one's going to sit there and drag boxes around all the cars and the road signs and the pedestrians and the cyclists and all the buses and trains, whatever. No one's going to go there and start labeling all of that data. Similarly, let's just say you wanted to create a use case which no one's even thought of yet. For example, let's just say you wanted to create a computer vision algorithm that actually uses neural networks in order to detect crosswalks, pedestrians, and cars in video feeds in order to determine if cars are keeping enough distance from pedestrians on the crosswalk. Or if you wanted to detect people doing illegal parking downtown, anything. All these different use cases require labeled data, but there isn't enough labeled data because who's going to sit there and actually start labeling all these terabytes of data? Spend the days or the months to actually do all of that. Even crowdsourcing it sometimes doesn't work as well. And plus, it's not even just limited to that. There's also the problem that there's a huge gap between the machine learning experts and the domain experts who are creating the data. Like, for example, if we've got a domain expert, say an oncologist, and they're trying to create a data set and help the machine learning expert, because the ML expert isn't an expert in that specific domain, they may not be optimizing or creating the machine learning model in a way that's absolutely optimal for this specific use case in this specific domain. If they know the kinds of patterns and the kind of data that they're working with, they can really get their hands much deeper into that and personalize everything else they build to that data. But through Power AI Vision, we're able to empower that domain expert and allow them to do things that they never could have done before, including labeling data in an exponentially faster way. In fact, up to 10 times faster is what IBM says. And of course, we allow them to train the machine learning models themselves with the help of the machine learning experts so that we're getting the most optimal models possible. In fact, unfortunately, while I won't be able to show you a live demo of the system in action today, I would love to show you a video demo of the system in action. So let's take a look. Now, it starts off in Power AI Vision. And remember, this is the domain expert doing this. This is not a machine learning expert. What they're doing is they're creating a very small data set. And this data set actually has one video, and it's just a few seconds of a clip. And it's a drone security surveillance footage. All right, so this is, let's just say this is a mall parking lot, and you've got a drone that's doing some security surveillance. This is the video that's coming through. Now, the domain expert has just extracted one image of a frame from this video. And what he's going to do now is he's going to label all of the parts of that image. He draws a box around the person, labels that as a person. Draws boxes around all the cars, labels those as cars. And then once he's done all of that, and once he does that for a few frames and creates a very small and limited data set, he then exports that data set back into Power AI Vision. Once that data set is in the Power AI Vision tool, he trains a model on that small data. Remember, this is very, very small data, so he's going to get a very bad model. A model that, forget production, isn't even ready for testing yet. But what the model will allow him to do is create more data faster. And so what he does now is, once the model is done training on Power AI, again, we're using Power AI, so it's extremely fast, he then goes ahead and uses that model, uploads a longer video that he has not labeled yet, and guess what happens? Remember, there are no labels, and he could just sit there and start labeling, but instead he uses the machine learning algorithm he just trained to label that data for him. And once the machine learning algorithm has labeled that data, all he needs to do as a domain expert is go into that data, as he is right now, take a look at what the machine learning model did, and if the machine learning model made little mistakes, to fix them, basically audit the data. Make sure that, for example, if it missed a very simple tag, like this one over here, to tag those cars, so it gets better and better. And then it becomes like an infinite loop. Once he's done this, using the auto tag feature, he has very quickly created another data set. He can then take that data set, go back into Power AI Vision, train a new machine learning model, and once that's done, create even more data, even faster. And then once that's done, within minutes, he can create a model that is good enough for testing, and eventually, over the course of a few days maximum, a model that is good enough for production. As you can see, this is data that the model has never seen before, and it's successfully able to label the car and the person in that video. So that was a quick demo of how you can actually use Power AI Vision as a domain expert in order to train machine learning models without having any knowledge of the underlying infrastructure, underlying code, and in turn, with the help of the machine learning expert, optimize the models and the data to get the most efficiency possible. Again, the advantages really just stack up here because we're using the Power 8 processor by IBM, which gives us a lot of advantages there. And we even have a very, very high rate of data transfer from the GPU to the CPU because IBM's NVLink, which directly links the CPU and the GPU, gives us 5 times faster speed there over the PCIe 3.0 communication protocol. And to put the cherry on top, it's hosted on the great Nimbix cloud as well. Nimbix allows you to host Power AI and a plethora of other cloud services as well. All right, so I hope you enjoyed that demo of IBM Power AI in action, and I hope that today I've been able to show you a sneak peek into numerous different technologies of the future, like quantum, but of course also deep learning, how you can solve one of the main problems with machine learning, that being the repetition that's involved, and at the same time, how you can actually use technologies like Power AI Vision in order to empower people like the domain experts who should be doing this kind of model training. Thank you very much, everyone, for joining in today. That's going to sum up my keynote. Thank you very much.